we changed the anchor point after we did it for the first one. Our anchor point was at 2, 4, and then we calculated the slope as I moved the dot along these different x values. So x equals 6, x equals 4, x equals -1. And we calculated the slope for all of these guys, right? And then we'd move the anchor point to an anchor point of 3, 9, and then we calculated those slopes for the anchor point being at 3, 9, right? Now what I want to do is, for this function that we've been dealing with this whole time, y is equal to x squared, I want to make a generic anchor point. I want to anchor this. I want to anchor this at my point x. Okay, at my point x. If I do that, by the way, and I call this anchor point, instead of x equaling to 2 or x equaling to 3, I'm just going to say x equals to x. Do you guys know what the y value would be for this anchor point? If my x value is x, do you guys know what my y value would be? Don't just say y, right? Give it to me in terms of x's. What do you think that would be? What do you think that would be? And what I'm saying is, last time my anchor point was at 3, that's my x value, my y value was 9, right? And the one before that, my x value was 2, so the y value of that anchor point was 4. Looking at that, can you guys tell me, if my anchor is at x, can you guys tell me what my y value is going to be? A couple people already answered. Beautiful, Monica and Brian. It is going to be x squared, right? My anchor point for this one, if I'm going to call it this generic anchor point x, then the y value is going to be x squared, because that's what the function is defined as, right? And it'll change from problem to problem. If y was equal to 3x plus 4, then whatever that is, it will be my y value in here. So my anchor right here is x comma x squared. Okay, x comma x squared. Okay, and if I wanted to add some values and calculate the slope with that, right? So I'm just going to do it for a generic one, right? Some generic point. If you guys notice, these points were basically just whatever your x value was here plus a specific value. So this one was, let's say x was equal to 3 was my anchor, and then right here was x equals to 10. That's technically just 3 plus 7, isn't it, to get to that 10? Right? And this one right here was technically 3 plus 5, right? This one right here was 3 plus a -1, and so on and so forth, right, to get these x values. So what I'm saying is, we can just look at this generic point for my secant line. And my generic point is going to be whatever my anchor point is, my anchor point, which is x, and I'm going to just add some random h value to it, right? I'm just going to add some random h value to it. So to get, for example, that 10, it was just 3 plus 7. For any generic value, I'm just going to say I'm adding like some random number h to it. If that's the case, then the y value would be that same thing, x plus h, but now squared. I'm saying, what the heck are you talking about, Nakmi? H is just some random number, I'm saying, to cover up for all those specific values that you can try to add. So if I wanted to do at x equals 10, I would just say my h was equal to like 7, for example, right? It all depends on what this is and what this is. And all I'm writing right now is a generic equation to cover all possible points, right? So my anchor could be anywhere on the x-axis, and my generic point to help me make my secant line could be anywhere on that x-axis as well, plus h, right? So if my anchor was at x equals 6, and I wanted my next point to calculate my slope at x equals 10, my h would just be equal to 4. Does that make sense? Does that make it a little bit clear, what I've just written right here? This is just saying that this generic point is just some random point after I pick an anchor point. So it can be any value. I can just make a slider out of it, and it'll just say like, oh, I just want it over here. I just want it over there. Okay? The reason why I'm just saying that we've done this for all these points. We just don't label it that way. We just actually label it with real numbers. And if I wanted specific ones, I could just pick those numbers. What I'm saying is, if I do it as a generic value, I can create a slider for my h, and it'll cover all the values on this thing. Right? I can make it any possible value, right? So what have we done on the past ones? We've been calculating these slopes, right? We've been calculating the slopes of these secant lines, right? We've been calculating the slope of these secant lines. And what I'm trying to say is this, basically. This was like my x1, and this is like my y1. This is like my x2, and this is like my y2. And we've done that for all these points up here, right, with these anchor points of 3 and 9, but now I'm just doing it with these generic points, okay? Now, these generic points right here, let's take a look here, right? Watch this. So I was calculating the slope of these secant lines, right? And it was always equal to y2 minus y1 over x2 minus x1, okay? Now, check this out. Check this out. I can plug in those points, those generic points now, instead of just plugging in the values of those specific points, right? We're just plugging into these generic points. So the y2 is right here, which is going to be x plus h squared minus y1, which is x squared. Okay? This is going to be divided by x2, which is x plus h, minus x1, which is just x. Right? And if we do a little bit of basically this is all we've been doing for all these calculations up here. When you got 11, when you got 5, when you got 2, you're just plugging in those points, right? But now I'm doing it for these generic values, okay? And I know this looks like a mess, but we've dealt with algebra before, right? So we can simplify this using some algebra, right? So I have over here, this is the slope of the secant line, right? And I'm going to FOIL this out. X plus h squared is going to multiply out to give me x squared plus 2xh plus h squared minus x squared. That's what I get in the top there. You guys see that? If I FOIL or multiply this out right here, I get this. What is going on with my pen? That's weird. Oh my. Okay. Wow, that's freaking out there. Okay, I gotta figure that out later. Anyways, in the bottom, it only does that for my highlighter. In the bottom, I have here x plus h minus x, which the x's are gonna cancel out, and I'm just left with a h in the bottom. Okay. Simplifying in the top, the x squares are gonna cancel each other out. Can I highlight this without freaking out? Not so much. Anyways, we'll figure that out later. So I have here, right, canceling out the x squared terms. In the top for the secant line, I'm going to have here is going to equal to 2xh plus h squared all over h, right? Which if you look in the top there, I have a common factor of h. I can factor that out and cancel it out, right? So I can write this as 2x plus h, factor out an h that they both have in common. And then the h's over here, top and bottom, can cancel each other out. So I end up with the slope of the secant line being equal to 2x plus h. So what this represents, by the way, what does this equation represent here? So check this out, right? What we've just essentially done is written down an equation that will calculate the slope if I know where my anchor point is and I know how far away the second point is, right? The x right here, if you think about it, this x represents your anchor, right? So let's go back to this first one, right? What was my anchor for my first one right here? X was equal to 2. Do you guys see that? X equals to 2 as my anchor, right? So the slope of the secant line, I'm saying, is going to be equal to 2x plus h. Well, if x is my anchor, that's what I would plug in, right? My h is the difference from the anchor point to my next point. So if my anchor point is 2 and my next point is at 10, I'd say here h was equal to 8, right? H was equal to 8. Now check this out. What I'm saying is I've essentially created a way to calculate the slope if I just know what the anchor point is and how far away the other point is. So 2 times 2 plus 8, right? This 2 was the anchor point for this x. This 2 is what we calculated. This h is how far away the anchor point is from the x value that you're calculating your slope. So I'm saying that the secant for that slope, the slope of that secant line is going to come out to be 4 plus 8, which I'm hoping you see is equal to 12, which is what we got when we calculated the point regularly. Why is this such a big deal? Once you have this equation down, you don't have to calculate the slope like this every single time. You can just use this formula, right? Slope of the secant line is equal to 2. My anchor point is 2. how far away is 2 from the from the next point of 6? How far away is 2 from 6? And that's going to tell me that h in here is going to equal to 4. So that's what I would replace this h with 4. And I can write this down. This is going to be 8, which is the same as what I got when I calculated the slope by hand. So with this equation, if I have an anchor point and I have a distance h away from that anchor point, I can calculate the slope of that secant line. Does that make sense? Without having to do this slope formula. Look. You ready? I can calculate the slope of this secant line, 2, 2, with my anchor point being at 2. And how far away is 2 from 3? How far away is 2 from 3? That has a difference of 1. And when I calculate this out, I have here 4 plus 1, which is 5, which gives me the same slope as what I calculated over here. So what I've essentially done for this generic case is now calculated an equation that will give me the slope between an anchor point, any anchor point, and a specific distance, a specific x distance away. I don't even care how high that point is, right? That's what this equation does, is it calculates the slope no matter which anchor point you pick and how far away it is on the x value. You don't even care about the y value. Does that make sense? That's a trippy idea, is it not? Like, all I need to calculate the slope between any 2 points here, like let's say from here to there, if I want to calculate the slope of that line, all I needed is the anchor point and how far away it is from the anchor point. Does that make sense? I don't know if that makes sense, but it's just a trippy fact that what we've essentially calculated, this equation right here, is this generic slope equation, and it will be for any points on this graph. And I don't even need the y value of it to do it, right? I just need the x values. I just need to see how far away it is, okay? And if I have that now, I can calculate the slope from here. I can calculate the slope from here, here, or here. Any of these dots, right? As long as I know how far away it is from your anchor point, okay? Now, as that gets closer and closer, as let's say my anchor point is at 2 here, as I get closer and closer to it, geez, my lines are terrible. As I get closer and closer to it, my slope gets closer and closer to it, to the a line that's going to be pretty much at 2. Do you guys see that? Pretty much at 2. Do you guys know what type of line that is if it's only touching at one point? If you have a line that's only touching at one point, do you guys know what that's called? When you have a line touching at just one point. Somebody typed it into the chat for me, or nor? No, is what I think you're saying there. Tangent. That's it, David. It's a tangent line, right? So here's the thing. Have you ever thought about calculating the slope of a tangent line? And if you know by the definition, a tangent line only touches at one point, yeah? But in order to calculate a slope, you usually need 2 points. You need x1 and you need an x2. So if I ever asked you to calculate the slope of a tangent line, it seems almost impossible because you only have an x1 and only an x1. You don't have an x2, right? But what we've essentially done here with this equation is we found a way to calculate the slope without caring about x1 and x2. We found a way that only cares about how far away is one point from the other with using this h, right? H represents the distance from x1 to x2 essentially, yeah? And you'll say, yeah, knock me, but you still need that second point to see what h is, right? I'm saying we don't. We spent a whole chapter learning about limits, did we not? Right? And what we're going to do now is apply the idea of a limit to this problem, right? If I have here the slope of a secant line, if I approach this function with the limit, I'm going to write this off on the side over here. If I take the limit as h approaches 0, right? What that essentially is doing is then the distance between the 2 points is going to approach 0. And as the distance between those 2 points approaches 0, right? I'm going to have here of this function 2x plus h, right, is going to be equal to just 2x. That 2x now, oh, okay, it's okay, it's recording so she can watch the video, but thank you for letting me know. That way I know that she's not just ditching my class. What this is essentially saying is then this is going to give me the slope of a line that's tangent to this function at any specific value of x, of any specific value of x, okay? You're like, Naki, what is this all that you're saying here? This idea, right, of taking the limit as h approaches 0 is going to help me figure out an equation that will always tell me the slope of a line that is tangent. I know some of you are like, what? And just put that on hold for now. Just put that on hold for now. And let me show you what I mean, right? Let me show you what I mean. You guys copy down this generic function. Go ahead and copy down this generic function. I'll give you guys a second. Here's my generic function. F of x, y is equal to f of x. It's some continuous function right here. Okay? Here's my continuous function. I'm going to call this right here my anchor point. This one, my new anchor point. Where's my anchor point happening at? It's happening at x, which is some random point I picked, comma f of x, because it's the value of it evaluated, the function value of it evaluated at x. Okay? Evaluated at x. All right? Now, let's say I wanted to calculate the slope of the secant line of some generic point, right? Let's call this generic point x plus h. Right? I've moved a generic distance h away from x, right? And I'm going to calculate the slope of that said secant line, which is going to be the secant line right here. Okay? So if this is x plus h, then this is going to be f of x plus h. Okay? So how do I calculate the slope of the secant line? Well, again, it's just going to be my x2 and my y2 right here, right? So the slope of this guy is going to be equal to, let's write this out, y2, which is f of x plus h, minus y1, which is f of x, divided by x plus h minus x. That's my x2, that's my x1, right? So the slope of this secant line is equal to f of x plus h minus f of x divided by h, right? That's the slope of the secant line for this arbitrary point to this arbitrary anchor point, okay? Now, in calculus, though, what we care about is at an instant, at a specific point, right? So I wanted like the slope of like a tangent line. I want this one right here. So what I could essentially do is keep making my h smaller and smaller, keep getting it closer. So here's one h. As it gets closer, the tangent line looks like this now. And I move that my h to make it smaller to here. So then that secant line looks like that now, right? And as I keep doing that, do you guys see how it gets closer and closer to what the actual tangent line looks like, right? As my h gets closer and closer to 0. So what that entails is this right here. What that entails is this right here. If I was looking for the slope of the tangent line, at that point right there, it's going to be equal to this function that we just found, right, to help us find the slope of a secant line. But it's very specific. It'll only happen as the limit of this thing as h approaches 0. That's what we need to do to calculate the slope of a tangent line. And that right there that I've written out is this fancy word that you've probably heard of as you know, the first time you heard what is calculus, right? We call this thing right here, we call this the derivative. We call this the derivative. How many of you guys have heard that word before? The derivative is pretty much what you're going to be doing the majority of calculus. But that idea of the derivative comes from the fact that you have to take the limit as these 2 points get arbitrarily closer to each other, to the point where it just does not have any distance between the two of them. Now, why do we have to take that limit? If you don't take the limit and you try to calculate the slope of a tangent line, you end up with, you know, x1 minus x1 in the denominator and then y1 minus y1 in the numerator. And you end up with this thing that's like 0 over 0. And you want to calculate the slope, but you know that it is defined. The slope of the tangent line is clearly marked. But if you do it this way, you get something that's undefined. If you do it using limits, that allows us to see what that tangent line approaches. And seeing what that tangent line approaches will give you this output value for that slope of the tangent line at any point on there, of any point on there. You're like, what is going on? Let me try to give you a visual representation while you guys write that down. Give me a second. Let me see if I can find my Desmos thing of this, and I'll show you what I'm talking about. Give me 1 second. Whoops. So while you guys get a second to copy that down. I might not have it actually. Give me a second. I might not have it. I thought I had one designed, but I might have to show it to you next time. But that's. Yeah, I might have to show you that next time. I'll get the graph of it created next time, but I just need you guys to write this down right here. This is what a derivative is. If you think of the word derivative, you're just calculating the slope of a tangent line at a specific point, and it's the limit as h approaches 0 of the function of f of x plus h minus f of x, all divided by h. Okay? Darn it, I really wish I had that ready. Why did I not have that ready? Give me 1 second. Let me see if I can find it. Give me 1 second. Give me 1 second. Nope, that's not what I want either. All right, well, I'll just have to create that next time. But yeah, so that's all we've essentially done here is we've calculated this derivative now that we can figure out what is the slope of any given tangent line at any point of a function. And I have just enough time to do one example of that. No, you know what? We're going to do that next time. I just wanted to show you guys that this is the limit definition of a derivative. But you know what? I'm going to actually just waste the last 6 minutes here just to show you what that looks like. And I hope I can do this on the fly. If not, I apologize. But let's take a look here. Let's see if I can do this. I don't actually know if I can. Okay. Okay, give me a second. One second. All right. Here's a graph of the function we were doing earlier. Y is equal to x squared, right? And I have the anchor point right here at 2, right? My anchor point here is at 2. We calculated our slope by using this formula right here, right? We let m equal to y2 minus y1. So it was usually like f of 10 minus f of 2. And then this whole thing was going to be divided by 10 minus 2. So give me 1 second here. I wish I had this ready, but I'm sorry. 10 minus 2, right? And we had the slope here that was equal to 12, right? And the way that looked was, can I do this real quick? Y minus y minus 2 equals to m times x. Oh, it was minus 2. Hold up. Y minus f of 2 x minus 2. There we go. Okay. All right, we calculated the slope of this secant line that connects it from here down to there, right? I swear I did this before, but I guess I didn't. And what I was saying was that I don't want this. I want the slope of the tangent line all the way down here at the bottom here. And what we could essentially do is change it, instead of making it at the point of 10, right? We can get closer and change that value to, let's say, 6, right? You don't have to write this down. I just want to show you. So if I change that to 6, you see now I come down to here and it has a slope of 8, right? Right? We can get even closer. Instead of 6, we can go and make that 5 and make that 5, right? And it gets closer and closer. Now, here's my thing, though. What I'm saying is, instead of doing that, and changing and calculating the values over and over again, gets tedious, is we pick some random number, right? Some random distance away, right? And we let that equal to h. We let that equal to h. So as h is, let's say, 8 away, right? Like that point right here, right? We can see that it has this line right here. But what I'm saying is, as I make h smaller and smaller, and I take the limit, as h approaches 0, look at my slope. You guys see my slope there? It's changing along the way, right? It's approaching a value, right? And what that value is approaching is the slope of the tangent line if h is equal to, well, in this case, it's 2. I should have did a better job. I messed up on this whole setup of it right here, but you guys see that right here? It's getting closer and closer to a tangent line, right? As I zoom in more and more here, as h gets closer and closer to 2, right? As h gets closer and closer to 2, I'm approaching a value for the slope of the tangent line right there. Which, by the way, what does it look like it's approaching? What does it look like it's approaching right there? It says it's undefined, but the slope is going at 4. It's at 5.3, and it's 4.8, 4.7, 4.6. 4.5, 4.2, as h gets closer and closer to 2. I'll do a better job this next time, but what does it look like it's approaching, the value is approaching at? What's the slope look like it's approaching? 4. Yeah, it is approaching 4. And in fact, if you guys take a look back up here, if I was looking at the slope of the secant line at x equals 2, right? At x equals 2, and I approached it as the limit of that approaches 0, I would get a value of 4. And that's it. That's the slope of that tangent line. Is 4, and we were able to calculate that thanks to limits, right? We can calculate the slope of that tangent line, and that's something that the calculator itself can't do. If it was actually just equal to 2 itself, right, it would be undefined. That's because it doesn't have 2 points to calculate it. But if it was equal to, let's say, 2.000001, right, look at that. That tangent line is right, that secant line is right there, and it's very, very close to that tangent line, and look at that slope. It's at 4. I'm saying that algebraically, we use limits and we can calculate that and see what it's approaching, and we'll get the exact value of the slope of the line at that tangent point. Okay. By the way, if I lost you at all at any point, just write this part down. This is what you need. This is the limit definition of a derivative, and this is what we're going to be using to calculate derivatives of functions, to calculate the slope of the tangent lines at specific points. Okay. Anyways, guys, I'm out of time. I wish I did this all at one go, but we'll talk more about this next time. Just copy down this equation, and that's it for today, guys. We'll continue this conversation tomorrow, okay? So with that being said, have a good rest of your day. I'll see you guys tomorrow, all right? Whew, sorry it was all over the place.